Welcome to the Explainer. So have you ever just stopped and looked at massive construction equipment or maybe enormous manufacturing plants or even rocket launchers and wondered, where all that incredible muscle actually comes from? Well, today, we're uncovering the invisible force that serves as the hidden muscle powering our entire modern world. We are talking about fluid power.
Think about it for a second. How exactly do we overcome our own frail human limitations to lift a gigantic force of, say, 36,000 tons, and doing it with nothing more than the delicate touch of a button or just a slight tilt of a joystick? I mean, it sounds like science fiction, right? Or magic? But actually, it's just brilliant, fundamental engineering.
Okay, let's dive into this. At its core, fluid power is all about the generation, control, and transmission of force using pressurized fluids inside a confined space. And this essentially splits into two main branches that you've probably heard of. First, we have hydraulics, which uses liquids, things like synthetic oils. And then we have pneumatics, which relies on compressed gases, usually just standard air.
Now, within this absolutely fascinating world of fluid power, we basically have two distinct flavors of systems, and they operate on completely different physics principles. On one side of the coin, we have hydrostatic systems. These use fluid pressure to transmit power, so they deal entirely with the mechanics of still, trapped fluids. But then, on the exact opposite side, we have hydrodynamic systems. These guys rely entirely on fluid motion. The power is transmitted by the actual kinetic energy of the moving fluid itself.
And this brilliantly illustrates that hydrodynamic concept. A hydroelectric dam is a perfect representation of pure hydrodynamics in action. We are capturing flow energy, literally the physical, kinetic movement of water rushing through those penstocks, to forcefully spin a giant turbine and generate electricity. In a system like this, the fluid absolutely has to be actively moving to do the work.
But when you contrast that rushing dam with a hydrostatic system, like an injection molding machine, it reveals a whole different ballgame. Here, the fluid isn't rushing past a blade at all. It's trapped. It's a static, still fluid confined under immense, punishing pressure. And it's exactly that static, trapped pressure that acts directly on a cylinder to drive those heavy, incredibly powerful actuators needed to clamp massive molds together.
So how exactly does trapped fluid generate so much raw force? Well, lean in for a second, because here is the fundamental secret of physics that makes this whole shebang possible. It's called Pascal's law. This law states that pressure applied to a confined fluid is transmitted undiminished in all directions. Basically, it pushes equally on all surfaces at perfectly right angles. It's such a simple, elegant rule, but it literally acts as humanity's ultimate force multiplier.
Now, what's really interesting here is how we can exploit Pascal's law for some extreme amplification. Because pressure, mathematically, equals force divided by area, if we apply a very small force to a really small piston, that exact same pressure travels completely undiminished through the fluid to a larger piston. So if that output piston has 10 times the surface area? No way, right? But yes, your output force is literally amplified 10 times. You push with just 10 pounds of force, and magically you can lift 100 pounds on the other side. But hold on. You can't just get something for nothing in this universe, right? The law of conservation of energy tells us that energy cannot just be created out of thin air. So there is an inescapable trade-off here. To multiply your force by 10, your smaller input piston actually has to move 10 times the distance of the larger output piston. You gain tremendous earth-moving force, sure, but you have to sacrifice distance to get it. That's just the beautiful, rigid math that governs every single fluid system.
Let's move along and see how this builds. How does all this abstract physics actually translate into the anatomy of a living, breathing machine?
If we trace the power flow through a typical system, it always starts with a prime mover, something like an electric motor, and that drives a pump. That pump draws oil right out of a reservoir, pulling it through a filter to make sure it's perfectly clean, and then pushes it out into the system under extremely high pressure. This pressurized fluid then travels through a directional control valve. Think of this valve like the brain of the operation. It directs traffic left or right. Finally, the fluid flows into the actuator, like a double-acting cylinder which does the actual pushing and pulling. And once the heavy lifting is done, the low-pressure fluid just loops right back to the tank to start the whole cycle all over again.
On paper, it's a beautifully simple, closed loop. However, while fluid power is essentially a mechanical superpower, bringing it off the whiteboard and out into the gritty, real world means we have to navigate some very strict engineering trade-offs and physical realities. So the crucial point is weighing these incredible advantages against those messy realities. On the plus side, these systems offer effortless force multiplication. They're super economical, and they give us incredibly accurate control of massive weights, even at low speeds. But working with oil and immense pressure can be tough. We have to deal with fluid leaks, which can literally make a factory floor incredibly slippery and messy. Then there's the very real danger of severed lines. I mean, when fluid is under that much pressure, a break is a major safety hazard. And finally, these systems are temperature dependent. A change in the oil's temperature actually changes its viscosity, which can completely alter how smoothly the entire machine performs.
But you know what? Despite those rigorous challenges, engineers have mastered these systems so effectively that this invisible force is quietly operating all around you, right at this very moment. It's in almost every facet of our daily lives.
This exact same fundamental physics is at work in a wildly diverse list of applications. Think about it. The same hydraulic principles that give you that smooth, effortless power steering in your everyday car, they're also used to deploy the heavy landing wheels on commercial aircraft. This tech is used in giant excavators digging city foundations, in cutting-edge robotics assembling our electronics, in military missile launching systems, and yes, it is even the raw muscle powering those massive high-speed amusement park roller coasters you ride on your summer vacation. It literally is everywhere.
Which brings us to our final thought for this explainer. We've seen how hydrostatic and hydrodynamic systems work, we've decoded the absolute genius of Pascal's law, and we've toured the anatomy of these living, breathing machines. But I want to leave you with this thought. If fluid power can multiply our fragile human strength to lift 36,000 tons with complete precision today, what other human limitations will this invisible force help us shatter tomorrow? Honestly, the next time you walk past a construction site or see a piece of heavy machinery, I hope you look right past the steel and recognize the brilliant, pressurized fluid doing the real work inside. Thanks for joining me on this explainer, and keep exploring.